Hey everyone, Eric Archer here from TI, and today we're going to talk about the most important thing in every human's life. I know what you're thinking. It's not the internet, it's not your phone, it's not social media, it's not video games, and it's not your favorite sports team. It's water. That's right. It's water. And without water, all of those other things don't really matter anymore because you wouldn't be here. In fact, the average adult can't survive more than 3 days without water. So you use it to bathe, brush your teeth, cook, wash clothes, wash your pets. Farmers use it to grow crops, and ranchers use it for their cattle. Water is what you are primarily made of. So that's right, you are mostly made of water. So about 60% of you is water. And the average human adult brain is about 70% water. So shouldn't we all understand how water works in our environment? And that's what we're going to do today. Today we're going to learn about the water cycle and how water sort of cycles through, on land and then up into the sky in the form of clouds. So water can evaporate, driven by mostly the sun and humidity. And once it gets up into the upper atmosphere, it can condense into clouds. And then once it condenses to a certain amount, it'll start to fall back down to Earth in the form of precipitation. Rain or snow or hail or sleet. And so water constantly is cycling, and water is very important to us, as you know. And so we want to make sure that everybody understands how this whole water cycle thing works. We're also going to talk a little bit about the possible side effects of global temperature changes on the ocean levels. There's a nice simulation that sort of simulates what's going on there. So before we get started, I encourage you to go to our website at www.education.ti.com to download the TI-Nspire CX Premium software. And then also go to our content site, which is www.scienceinspired.com. And that's where you can find this activity, which is titled The Water Cycle, under the category Earth Science. And we have a bunch of science activities there for middle school and high school. All right, with that, let's go ahead and get started. Throughout the video, you're going to hear the term hydrologic cycle. That's just a more formal way of saying the water cycle. It's the same idea, just a different name. But the hydrologic cycle is basically the interaction of the atmosphere, which is sort of where the air is, the hydrosphere, our planet's water, and the lithosphere, the land. And so those three areas interact and sort of have an effect on what happens to water as it cycles through various phases. And then throughout the hydrologic cycle, water can exist in any of the three states. It can be a solid, liquid, or a gas. And you've seen all of these. So a solid would be ice, liquid would be liquid water that you can fill up a glass and drink. Gas would be water vapor. So if you've ever boiled pasta or boiled eggs or something like that, the sort of the white steam that's coming up, that's all water vapor. Okay? Okay, so now we're in the software, the TI-Nspire CX Premium software. Again, you can get that from our website. I have the file called the water cycle opened up within the software. And the first picture you see is a geyser. And so we're going to run through a series of questions, and then we'll end up hitting a couple of simulations to sort of model the hydrologic cycle. All right, let's go to the next page, 1.2. Just to lead off, water in the ground is part of the hydrologic, the water cycle. Is that true or false? Of course, this is going to be true. Okay. Moving on. Condensation is when air turns into a liquid. So condensation is when water vapor turns into liquid water, but it's not when air turns into liquid water. Air is made up of, there is water vapor in air, but air is actually made up of mostly nitrogen and oxygen, and then some other gases like CO2. So condensation is when water vapor turns into to liquid. And page 1.4, there is less water on Earth now than there was 500 years ago. So think about that. So if we're talking about a water cycle, that means that the water is going, just kind of in one form to the next, and then on back into the form it started in. So there's probably no more or no less water than there was 500 years ago, so we're going to say false on this one. And finally, that brings us to our first simulation. It says the directions are: move the mouse over the landscape to see the different stages of the hydrologic cycle. Note the movement of the water and think about which phase the water might be in for each of the 5 phases. And then find the following stages. So let's see, we have evaporation, condensation, precipitation, runoff, and infiltration. So we're going to go ahead and explore those. I'm going to close this menu box out. Alright, so right now we have, looks like evaporation, so we have this sort of mountain with a little stream flowing down into, maybe this is a river flowing into the ocean. And so evaporation, sun changes water from liquid to gas that rises into the atmosphere, so the little white circles rising up represent water vapor rising in the air. Of course, you can't see this in the real world. You know, during a hot, steamy day, if you take a bottle of water and pour some of it out onto a hot sidewalk, you wait a couple of minutes, that water won't be there anymore. It will have evaporated. And so that's what we're talking about here. Let's move on here. We see runoff, so precipitation or snow melt. It's like there's some snow melt on the top of this mountain, moving over and through the ground. So runoff's pretty common. You can actually simulate this just by getting one of your parents' not so nice containers, like a Tupperware container, big size one, and filling it, about half of it up with some dirt, and leaving the other half sort of empty, and then just take a water bottle and gently pour water across the dirt and just sort of watch what happens. But that's the same idea here, is that there's runoff going through the land and back into the water because of gravity. Other hot spots here: infiltration. Okay, so water soaks into the ground, becoming groundwater. So same thing, you go outside with a water bottle, and instead of pouring a little water on the sidewalk, you pour it into some grass, some dirt area, and you wait a few minutes. At first that dirt will be wet, there will be water sitting on top of the dirt, but eventually it'll get soaked in, it'll infiltrate the ground, and large amounts of water that do that, they'll end up becoming groundwater. Okay, let's see what else we have. Precipitation. Water from the atmosphere returning to the lithosphere. Remember, lithosphere means land. Rain, freezing rain, sleet, snow, hail. Those are all forms of precipitation. Basically, water that had evaporated, formed in the clouds. The water vapor in the clouds condenses into liquid water, and that liquid water ends up falling back into Earth, maybe as freezing rain, ice, sleet, snow, and so on. And then finally, condensation. So water vapor in the air changes into liquid water, forming clouds, fog, dew, and so on. So that's the other thing. So when air masses hit one another, like cool air masses and warm air masses, you get cloud formation, you get some condensation of water, storms form. It's pretty fascinating, but the water cycle is a big part of all of this, and a big part of what the weather does. So interesting stuff. All right, so the next several slides are going to ask you questions about what happened in the simulation. So we're going to go through those. In which state or states does water exist during precipitation? And so we have some options here: solid only, liquid, or gas, liquid or solid liquid, and gas. So for precipitation, we're talking about things like snow, which is a form of ice, hail, which is a form of ice, rain, which is obviously water. So really the only answer would be liquid or solid. Page 1.7, in which state or states does water exist if it has been condensed? So let's see. So the only way you can condense H2O is when it's in its gas state. So you can't condense liquid, you can't condense a solid any more compactly than they're already condensed. So really the only thing you can condense is a gas. So remember in that simulation, where was evaporation? So evaporation, water is in its gaseous state, and then it cools off because it's cooler up here in the upper part of the atmosphere. And because of how cool it is, the evaporation will condense back into a liquid or a solid. It could condense into ice as well. So in that case, the only thing that can be condensed, the only state of matter, is gas. Okay, next page, 1.8. Clouds are made of what? Liquid, gas, or condensed air. So they're not made of condensed air. They're not made of gas, although that's what you might think because they're like these big puffy things floating through the air. But the actual answer is they're made of liquid. I mean, that's the cloud formation. That's where those clouds get big enough and the temperature is just right, and the water condenses to a point where it starts to fall as precipitation. So clouds are actually made of liquid water, which is pretty cool. Page 1.9, into which state or states is water changing during evaporation? So remember that simulation? I'm going to jump back up there real quick. I think we were right here. So the sun's sort of heating up the surface of the earth. The surface of the earth includes the lithosphere, the land, as well as the hydrosphere. And water is sensitive to temperature changes. And so when you heat up a pot of water on the stove and you boil it long enough, it'll eventually turn into steam. And so a more subtle version of that, I guess, is when the sun heats up the surface of the earth, and any water that's on the surface, if it gets warm enough, it'll turn into a gas from a liquid, and so that's what we're seeing there. So really, the only answer, for that one is that in which state or states is water changing during evaporation? Well, it's obviously got to be a gas only. All right, next question. In which state or states does water exist during infiltration? So, well, we look in the simulation one more time. I think infiltration was somewhere over here. There it is. So water soaks into the ground, becoming groundwater. Well, ice can't soak into the ground unless it melts first into water. And gas is going to be rising, not infiltrating. So the only answer there is liquid only. And finally, can water exist as a solid in the atmosphere? Yeah, I mean the answer is actually yes. You wouldn't think it would. You'd think, yeah, it's too dense, too heavy. But yeah, it can. I mean that's kind of how snow and hail are formed, is sort of this constant cycling that's going on up there with moving air, very cold temperatures, and so water droplets end up becoming ice, little particles of ice, and over time they keep building and becoming bigger and bigger chunks of ice, or flakes of snow, and then they'll eventually become heavy enough that they'll fall to the earth. On page 2.1, it's introducing you to sort of a new concept related to the water cycle. Let's go ahead and read through it. It says there are many places where water in the hydrologic cycle is stored. Water can be stored in ice caps, glaciers, aquifers, lakes, rivers, and oceans. In this next simulation, you'll investigate how increasing the average atmospheric temperature affects the storage of water in the hydrologic cycle. So just some lead-up questions that just to make sure you're understanding where we're going here. If the average global atmospheric temperature increases, what do you predict will happen to sea levels? And so this is really your prediction. And we'll find out here in a few minutes. So I'm going to keep moving. Next question, predict what might happen to the severity of storms as the global atmospheric temperature increases. So will storms become more severe, less severe? Really no change in storm severity. So just something for you to think about as we go into the actual simulation. So this one, it says, select the average global temperature of the Earth, observe the effect on sea level, and observe the effect on the average number of severe storms. All right, so the way this works is we have a little temperature. We can change the temperature up or down this way. Intense storms, on average, this is an average number. Obviously, you can't have 7/10 of a storm. But in 20 years, the intensity of the storms is 0.7. And temperature 57.2 degrees Fahrenheit currently in this particular scenario for the simulation. And just to sort of add some additional background, the simulation uses the 20th century average of 14.8 degrees Celsius, which is about 58.6 degrees Fahrenheit, with the EPA predicted 6 degrees Celsius increase over the next 100 years. Now, those numbers, depending on which researcher's doing it and what year you're checking in, can change a little bit. So just understand that simulations try to model what will happen, but simulations are limited to our understanding of a system. The climate is a very complex system, lots of variables, lots of things we're still learning about. So just keep that in mind, that although simulations try to represent what will happen, sometimes they're not quite on point. But let's go ahead and mess with this one anyway and see what happens. So we start off at 14 degrees C. Notice the temp number, the intense storms number. We're going to bump that up a degree. Looks like the intensity of storms is going up a little bit. Average global temp went up, and I think you might have noticed the little sea level rise there. Okay, so your beachfront property just disappeared. And we're going to bump it up to 16 degrees Celsius. Same thing, a little bump in intensity, storm intensity, and temperature. If we go 17 degrees, sea level's rising, storm intensity's up. And I'll keep going up here. I think it might be Kevin Costner in the background there from Waterworld. That was a joke. He's not really there. So it looks like 21's the max, and the storm intensity is up to a 3.0. Global average temperature is at 69.8 degrees Fahrenheit. Depending on where you live, that actually might be quite pleasant, or it could be, could really cause some problems. So, so there's, just a little model of what could happen. Some possibilities here based on what we know from the EPA. And the EPA and those incredible scientists, they're, like I said, they're researching this stuff all the time, and as a result, the more information they learn, the data may change a little bit. So let's see, page 2.5, what happens to the sea level as the average global atmospheric temperature increases? And so you notice that as the temp increases, this model, this simulation, shows that it's possible that the sea levels could rise. Okay, page 2.6. Which of the following is the most plausible hypothesis for the increase in sea levels? Which looks like I have a little typo in my file here. Let's change that real quick. Look at that. Done. So which of the following is the most plausible hypothesis excuse me, for the increase in sea levels? And so you have some options here. There's an increase in the amount of precipitation. The ice, snow, and permafrost stored in the hydrologic cycle are melting. Storms are more severe and occur more frequently. So, some of these seem pretty reasonable. Increase in the amount of precipitation, but maybe that also implies that there's an increase in evaporation and that the water cycle is just cycling through more quickly. That doesn't necessarily mean the oceans are going to rise. The second one, the ice, snow, and permafrost stored in the hydrologic cycle are melting. Well, melted ice turns into water, which could explain why there's more water in that simulation there. So that's a possibility. And storms are more severe and occur more frequently. Again, that doesn't necessarily cause an increase in sea level. So I'm going to go with the middle one. The ice, snow, and permafrost stored in the hydrologic cycle are melting. It also seems reasonable too that if your temperatures are rising, then any water that's been stored in permafrost or ice is probably going to melt and turn into liquid, which would raise the levels of raise your sea levels. All right, page 2.7. Based on the simulation, what is predicted to happen to the number of intense storms as the average global atmospheric temperature increases? And so we saw that already. We'll go back. So as we bump up the global average temperature of the planet, you'll notice that the intensity of the storms, as shown here, increases. So we'll bump that back up. All right, more severe storms. Oh no, that's not good. And so so it looks like the number of intense storms will increase. The number of intense storms will decrease. The number of intense storms will stay the same. So we're going to go with increase. So it's a nice model because it shows you that everything's sort of tied to everything else from a weather point of view, water cycle, global temperature. Everything kind of is tied together. And the last question of the activity, what do you think is happening to the rate of evaporation and condensation as the average global temperature increases? And so, you know, we notice that if there's more intense storms and the water is increasing, then I think it stands to reason that the rate of both are going to increase. The rate of both the evaporation and condensation will also increase. You know, the severity of precipitation events will also increase. So the water cycle will just be kind of moving a little more quickly, basically is what would probably happen. All right, well that's the end of this activity. I hope that was helpful to you. You can download the student and teacher documents at the website at www.TI-Nspire.com. Look under Earth Science and then check under the water cycle and you'll see all of those PDFs available to you. And you know, if you think your teachers might be interested in this, have them check it out and they can edit the student documents to make it their own. All right, with that, again, I hope you learned a lot about the water cycle, the hydrologic cycle, and you come back and watch some more videos and check us out. Thanks a lot. Have a good day.